Welcome back. We're going to look at the next part of our calculations here that you are responsible to be able to do and perform throughout the lab and on the lab exam. If you recall, we left off calculating our total red blood cell count, and we said based off of our sample from the practice problem that our total red blood cell count for a given sample was 5.5 times 10 to the 6 RBCs per millimeter cubed of blood. And we're going to take this value right here, and we're going to use that to help us calculate out the mean corpuscular volume for a given sample. Now, part of being able to do this is dependent upon being able to calculate the hematocrit, which we know we're going to take one of those little capillary tubes that you see that you saw in the lab. Right. We're going to measure out the total distance, the total height of that tube in millimeters. So that's the total height. Right. And then we're going to also measure the height of the packed red blood cell volume. Right. And so what's the height of that in millimeters? And we're going to take the red blood cell height. We're going to divide that by the total, multiply by 10, and that is going to give us the hematocrit, which we will then plug into our equation. And so for our sample, for our example, we're going to suppose that we went through and we calculated out the hematocrit, and that hematocrit was calculated at 40%. And we simply plug in the rest of the equation, which is going to be times 10, divided by the total red blood cell count, which is what we found on the previous calculation that we did when we did total red blood cell count. And so we defined that, or we calculated that out as being 5.5 times 10 to the 6th RBCs per millimeter cubed of blood. For convention, since we're not going to end up in times 10 to the 6 RBCs per millimeter cubed of blood, if we were to cross multiply, this here would simply disappear our units. And so that's exactly what we're going to do. We're going to make that disappear. MCV is then going to equal 40 times 10 divided by 5.5. 40 times 10 is 400 divided by 5.5. And if you're doing this math on your phones or whatever it is that you're using, you're going to come up with an answer of 72.73. Remember that our unit of measurement is femtoliters, which equals times 10 to the negative 15th per RBC. This represents the volume, the average volume of a red blood cell. Right, so the lower the average volume of the red blood cell, that signifies that the red blood cells are smaller, which means they're not going to be able to transport as much oxygen because they have a smaller volume. And in fact, 72.73 is below the normal range for the volume of a red blood cell. And so this here would simply indicate that this individual here has an iron deficiency due to the fact that the red blood cells are microcytic. In other words, their average volume is smaller than expected, and therefore there's fewer red blood cells, smaller red blood cells, not able to carry enough oxygen due to a lack of hemoglobin. All right. And so that is your mean corpuscular volume. Now, mean corpuscular hemoglobin is going to be slightly different. Here we are measuring the average weight or the average mass of hemoglobin. All right, that is what we are looking at by mean corpuscular hemoglobin in a red blood cell. And so, in other words, is there enough hemoglobin to actually carry the oxygen? And so, in order to do that, we see our equation. Right. Hemoglobin, which is measured in grams per deciliter, times 10, divided by the total RBC count. And so let's go ahead and let's look at this as a mathematical example. All right. MCH is going to equal our hemoglobin. For this one, I'm going to have to give you because we're not actually calculating out hemoglobin in the lab. And so this is, we're going to use as an example, 13 grams per deciliter is our hemoglobin times 10 divided by our total red blood cell count that we have already calculated, 5.5 times 10 to the 6th RBCs per millimeter cubed of blood. But we know that we're just going to simply ignore that. So we don't have to worry about that. And so now we're just dealing with essentially 13 times 10 divided by 5.5, which equals 130 divided by 5.5. And if you're still doing the math, 23.64. But remember that our mean corpuscular hemoglobin is measured in picograms. So this is pg per red blood cell. And in fact, this value here is below the normal range. And so this here is also confirming, besides being low, that this person has an iron deficiency. And this would basically be hypochromatic or hypochromic, meaning a lack of color. And the reason why these red blood cells would be lacking color would be because of a very, very low amount of hemoglobin. The iron is what gives blood its red color. All right. If this person was pernicious anemia, we would see this value being between 33 and about 53 picograms. And the cells would be larger because that is what pernicious anemia is. You get these very large cells that are immature, and so they're not fully capable of being able to carry enough hemoglobin, but they're carrying some, and so therefore it gets to be a palish red color, more on the pinkish side than a true red color is what you would be experiencing with the blood. And so that is how you do these calculations. We have looked at doing calculations now for total red blood cell count. We've talked about the calculations for hematocrit. We've talked about the calculations for mean corpuscular volume and mean corpuscular hemoglobin. I would suggest that you continue to do some practice problems with this. All right, you've got some practice problems that I've posted for you as well. And of course, I am always available for any questions.